All right, so welcome to everyone who's joining on YouTube as well as joining us live. We're going to start with chapter 1, but we're really going to go chapter by chapter, and I've recruited a number of amazing volunteers to summarize each individual chapter and then present it to the community. I've summarized kind of a few and presented a few different books before, and I think it's really given me an interesting perspective on the book, and I remember something much better when I presented it to others. So hopefully our volunteers will feel that benefit. So chapter 1 was just an overview of machine learning systems. Yeah, machine learning, I think, is something that people are hearing quite a lot about these days. But let's just start with the definition. So it's an approach to, one, learn complex patterns from existing data and use these patterns to make predictions on unseen data. So there needs to be something to learn. It's not just a lookup table, right? And generally more helpful when they're complex patterns, but there does have to be something to learn, so it can't just be completely random. Like, there's no point in building a machine learning system to predict the roll of a dice. And it does really need typically quite a lot of data. Yeah, there are kind of topics such as few-shot learning and zero-shot learning, which we'll maybe discuss as well. Can you build a machine learning system that will learn with very few examples, but that tends to be quite tricky to do. And so yeah, machine learning is especially helpful if a task is repetitive. So again, if there are lots of examples to learn from, or if the cost of run predictions is cheap. So like recommender systems, really great use case for machine learning, because if the recommendation is terrible, then somebody just won't click on it. It's not that big a deal. Self-driving cars, much trickier, but it can still be worth it if self-driving cars get to the point where it's statistically safer than a human driver, it can still be worth it, even if there might be, like one or two, even if there's a death caused by machine learning. Making the wrong predictions, if it's much safer still than human drivers, you could still say it's worth it. Yeah, and then obviously the other, I think, important point is that it does typically require lots of upfront investment to develop this kind of system. So it is very helpful if it's something that will be useful at scale, unlikely to be just a tiny use case on one day that you'll develop a machine learning system for. Chip Hugian then, and the book as well, also talks about machine learning in research versus production. This is, I think, very interesting to think about the different requirements. In research, you're just looking for often state-of-the-art model performance on benchmark data sets. So if you can get from 94 to 95% accuracy, then that's amazing. Whereas in industry, the stakeholders don't really care that much about, okay, necessarily have we got from 94 to 95. It's much more like different stakeholders have different metrics and requirements, and it's often more tied to the business outcome that they need to drive. So like, okay, has this actually made our customers happier? And a tiny percentage point in metric may or may not do that. And then we've also got kind of different computational priorities, just where often in industry, you have to think a lot about low latency. So we had that case kind of recently where we were just thinking about, really, can we use a much smaller model just in order to get the latency requirements down, because users don't want to wait very long for predictions. I think consumers especially have very low tolerance for that kind of thing. And then the data in research versus production. So in research, often you can just have a benchmark data set, which doesn't necessarily change, whereas in production, it's just constantly shifting. So that's just another thing you have to account for. And then fairness and interpretability in production, also you have to consider a little bit more, how are actual people going to be impacted by your model? And I did really enjoy this image from the book, which is adapted from a different image from Andrea Carpati, but just amount of sleep lost over data sets versus models and algorithms. So in during a PhD or in academia, you're really just thinking about very complicated models and algorithms. And the data is generally pretty clean. Whereas in research, so much of it is just trying to deal with really, really messy data. So that was kind of just a bit of an introduction into machine learning systems and just kind of the difference between designing for research versus designing for production. I'll pass it over now to Bruza, who's going to give us a chapter 2, so introduction to machine learning systems design.
Yeah, thank you, Silke. I'm gonna present today chapter 2 and chapter 3. Chapter 2, which is introduction to machine learning system design. Chapter 3 will be data engineering fundamentals. So shall we move on the next slide, please? Yeah. So we begin by discussing how business objectives should guide machine learning objectives. While, as Silke mentioned before, while machine learning engineers focus on optimizing accuracy, precision, and recall, business mostly care about real-world impact, like reducing cost, or increasing revenue, or improving customer experience. So the book highlights a crucial issue, which is machine learning engineers to focus on metrics, as I said before, but the business don't care about these numbers, they just care about the impact. So, for example, try to increase accuracy 94% to 94.2%. Seem like an achievement, but it doesn't drive business value, like increased revenue, then it's meaningless. So our key takeaways is every machine learning system must serve a business goal. So otherwise, it also risks becoming an expensive experiment. Yeah, shall we? Yeah, thank you. So now, for machine learning systems to be successful in production, it needs to satisfy 4 fundamental requirements: reliability, scalability, maintainability, and adaptability. Reliability, which is the model should work constantly across different scenarios. And scalability, it should handle increasing amounts of data and traffic. Maintainability, which is debugging and retraining, should be manageable. Adaptability, the model must evolve as data and business needs change. So, but there are some challenges, of course, and one major issue is data drift. Definition is model performance gets worse over time due to changing data. For example, a recommendation system for an e-commerce platform starts making irrelevant suggestions if the customer shopping behavior changes. So it's a challenge, one of the challenge. The other one is concept drift. The book said that in the definition, the relationship between input features and target outputs can change over time. For example, a fraud detection model trained on old fraud patterns may fail to detect new fraud techniques. And there is another challenge, feedback loops. The definition is the model accuracy declines over time due to data drift of concept drift. So, for example, a spam filter that fails to recognize new type of spam email because it was trained on outdated data. So the book explains a machine learning system is not just about model accuracy. It must be robust, scalable and adaptable to real-world challenges. Yeah, we can move. Thank you. So unlike traditional software, machine learning models require continuous improvement, as we talked before. So the book emphasizes an iterative machine learning development cycle, which starts with project scoping. So defining the business problem and determining if the machine learning is the right solution, for example. So in this step, we identify our goals, we check our data, if we have or not, and we try to identify our expected outcomes. So the second step, which is data engineering step, in this step, we collect, clean, and transform our data for modeling. Then we try to create features that enhance predictive performance. The third step, machine learning model development. In this step, we train our models using algorithms, and also we try to ensure our validation data, or we try to check our unseen data. For example, a sentiment analysis model classifies customer feedback. And the fourth one is deployment. So we integrate our model into production via APIs or cloud service. And we ensure, again, our scalability and real-time predictions. And the fifth one is monitoring and continual learning. So in this step, we detect data drift, concept drift, and feedback loops, as we talked before. And we try to automate our model if it is, to retrain if it's necessary. For example, a credit scoring model updates as financial behavior shifts. And the last one is business analysis. We try to in this step, we evaluate if the model delivers real business impact, and we adjust for bias, unexpected outcomes, or evolving business needs. And in this part, the book says why iteration is necessary. So the machine learning isn't a one-time solution. It's an ongoing process, as we saw in the image. So the models we train today will need retrain tomorrow. Why? Because environments change, user behaviors can shift, or new data also constantly emerge. That's why iteration is very necessary in machine learning models. So we can move So one of the key takeaways from the book is that many machine learning failures are due to poor problem framing. So machine learning should not be applied to problems it was never meant to solve. So problem is very important. Framing problem is very important. And common machine learning problem framing types, for example, classification and or regression. So if we want to predict categories like spam or non-spam, we can use classification problem. Or if we have a continuous values like precise price predictions, for example, we should use regression. Another one is anomaly detection versus supervised learning. So if our data is labeled, we should use supervised learning, but sometimes they don't have labels, so we should use unsupervised learning. In the book, also causal inference versus correlation-based learning. So are we interested in cause and effect relationships, or we just want to predict correlations between variables? Based on this, we should choose these types. For example, fraud detection. So anomaly detection looks like for rare, unusual transaction without predefined labels, but supervised classification requires labeled examples of fraud cases to learn from past data. So basically, choosing the right machine learning approach ensures that models solve the right problem efficiently. That's why it's really important. We can move the next slide. Yeah. So here's a conversion question. So mind versus data. Is it better to have complex model or better data? But which one is better? So many people assume more complex models are always better, but in reality, better data usually beats a better model. So yeah, in the book also emphasizes these hierarchy formats. So in the base layer, there's a step collect step. So which is the we are collecting the data, and it might come from websites track user interactions or devices collect sensor data, and then we move and store our data. So data needs structured storage, like databases, ATI pipelines, cloud storage. And the third one is explore and transform. So data cleaning, anomaly detection, and feature engineering happen in this stage. For example, removing duplicate records or filling missing values before model training. And then aggregate and label. So data is aggregated and structured for analysis, for example, metrics, segmentation analytics. Then fifth step is learn and optimize. Machine learning models are built, tested, and optimized at this level. For example, fraud detection models learn from labeled transaction data. And the last one, AI deep learning, top layer. The most advanced stage here, like A/B testing, experimentation, and deep learning models. So we can move the next slide. Yeah. So we talked about chapter 2. Now we're gonna talk about chapter 3. So machine learning models are only as good as the data they rely on. So the book highlights that at the end, I want to say poor data quality leads to unreliable predictions. So it's really important. And this chapter, we will explore data engineering fundamentals. We try to okay, let's move. Yeah. So introduction to data engineering fundamentals. So this chapter, we will cover data sources, storage formats, processing techniques, and data movement. And in the book says, why is data engineering important? Data engineering ensures that machine learning models receive high quality structured data, which improves performance of scalability. So that's why this step also very important. We can move if it's okay for you. Data sources, yeah. So machine learning systems depend on multiple source of data. So in this book, for example, there are user-generated data like reviews, text, images, system-generated data like logs, sensor data, and the third-party data like external APIs and open data sets. So data sources is important, and the challenges might be like we should ensuring data quality, consistency, and security. Noisy or biased data leads to poor predictions, for example, in the book said that. Handling large volumes of diverse formats is important. And as I said before, addressing privacy and security concerns is important, and it's a big challenge also. We can move if it's, yeah, thank you. So one of the most crucial decision in machine learning system is selecting the right data formats. So the book highlights that choosing the wrong format can lead to inefficiency in storage, retrieval, and processing speed. So that's why it's really important. And the common format one of them is JSON. It is human readable, but inefficient for large scale storage. For example, often used in web applications, but can become very slow for large data sets, JSON format. And there's a row major and column major storage. Row major, like SQL databases, and they are optimized for transactional operations where records are accessed by row. And there are column major also. It is more efficient for analytical queries. And there is a text and binary formats. Text, which is, CSV, JSON format. They are easy to read, but inefficient in size and processing speed. And there are binary formats, more compact and optimized for fast retrieval. And our key takeaways for this slide, the choice between row major or column major depends on whether we need fast transaction or analytical querying. And the binary formats are preferred for large-scale machine learning models because they optimize storage and speed. So binary make it fast. And the book emphasizes that selecting the right format is very crucial for system performance and scalability. We can move to the next one. Thank you. So once we have data stored in the right format, next the question is how we should organize it. So the book highlights three primary data models in machine learning systems. One of them is relational databases like SQL based, structured and widely used in transactional system, as I said before. And there is a document, NoSQL. They are more document-based system, document-based data models. They are more flexible schema they have, suitable for semi-structured data. For example, they are used by applications like MongoDB, which store data in JSON-like documents. And they are graph-based they are used for network relationships, such as social networks or recommendation systems. And for example, LinkedIn and Facebook, they are using graph-based data models. And there is structured and unstructured data. Structured data organized in tables with predefined schemas like SQL databases. And unstructured data, there are free form, they are in free form data such as images, text, and videos. So in the book, our key takeaways, choosing the right data model is crucial based on how the data will be used. For example, relational database work best for structured, financial, or transactional data. NoSQL is better suited for semi-structured data such as logs and documents. And the graph-based are ideal for relationship, for understanding complex relationships in the data. So choosing the right data models impacts on performance, scalability, and flexibility again. That's why it's important. And the next one is data storage engines and processing. So we select our data format and model. Now we need to consider how data is stored and processed. So the book categorized storage engine into two main types, transactional and analytical processing. Transactional databases, OLTP, optimized for real-time curate operations: create, read, update, and delete. They are optimized for real-time operations. And also analytical databases. OLAP, for example, optimized for large-scale analytical queries and complex aggregations. For example, Google BigQuery, Amazon Redshift. They have large-scale business intelligence queries. And I want to talk about shortly ETL process, which is basically move raw data into structured formats for machine learning models. It's really important. It includes pre-processing, filtering, and aggregation before data is fed into machine learning pipeline. So data storage engines and processing system it's a milestone of machine learning systems, because it ensures that models can work efficiently with large data sets. The last one, yes, thank you. Modes of data flow. So the way data moves through a machine learning system directly impacts performance, scalability, and real-time decision making. So the book categorized data movement into 3 primary models. One of them is data passing through databases. It's a traditional approach. How it works, data is stored in relational or NoSQL databases and accessed as needed. For example, a customer database where machine learning model retrieves user data before making recommendations. Data passing through services, they are more API-based processing. How it works, machine learning models receive data via APIs without requiring a full database retrieval. For example, a real-time recommendation system fetch data through APIs calls rather than storage, data storage. And the next one is real-time data passing. It is more event-driven processing. Data is processed as it arrives using streaming technologies. For example, fraud detection systems. It analyzes transaction in real time. So it has a real-time data streaming. So another crucial, the book emphasizes that batch processing and stream processing. Batch processing, which is data is collected and processed at scheduled intervals. For example, a Salesforce forecasting system process data from the past month to predict, the next month, for example. But the stream processing, data is processed in real time as it's generated. For example, a self-driving car, they process sensor data instantly to detect objects, or, as I say before, fraud detection in banking. They are also try to analyze the transaction data, they monitor the data, leave, and try to catch suspicious activity. So the book emphasizes that choosing the right mode of data flow also depend on the system requirements. So batch processing for analytics, stream processing for real-time machine learning applications, it says. And understanding how data moves is just really important as how we process it. So it's what makes machine learning system not just intelligent, but also efficient and scalable. Thank you.
Amazing. Thank you so much, Buzer, for
Thank
summary of those chapters.
So,
yeah, I'll hand it over to Eka now.
Yes, so I will go on. Like the chapter 4 is about training data. So it doesn't matter how smart and good your algorithm is if you don't have the good data, and if your data is messy, so you can't get good predictions. So this chapter, could you go to the slide? And there's this messy the biases which can be and the data can be caused by like processes in collection, sampling, and labeling. And in this chapter is like like discuss the importance of obtaining good training data and challenges related to labeling and the challenges to related class imbalances, because in a real world our data are really have like class imbalance problems. And then it discusses data augmentation techniques. Please go to and why do we need sampling? We need sampling because we can't access all the data, and if even we can access all the data, it's impossible to train them like work with all of them. It requires too much time and it requires too much resources. And the sampling allows us to accomplish a task faster and cheaper. And for example, if we consider a new model and we have small sample, we can experiment our new model on this small sample. And then if the experiment is good, we can just then experiment is a bigger sample as well. So, and the sample, how good is our sample when you train data is crucial, of course, and there are some different sampling techniques. I will not go. Could you please go on? And there are some non-probability and random sampling methods, and each of them contains some different types of sampling. And non-probability sampling is not so reliable because it tends to bias data. It's just easier to obtain some data. For example, convenience sampling is when data can be selected based on their availability. And an example of it could be like language modeling, when language models are often trained not with the data that is representative of all possible text, but they are trained on on texts which are easily collected, like with Wikipedia or Reddit. And when it comes to judgmental sampling, in this case, we need experts' opinion. And snowball sampling means when we have some small group of people and they refer to others So by this way, the group of our sample is increasing. We can obtain more reliable data if you do random sampling. One of the types of random sampling is simple random sampling, when we assume that when we give the same, for example, when you have classification problem, we can give each of a group the same weight. But weighted sampling is more realistic. It can give better predictions, but it just needs weighting sampling just needs prior knowledge of real data, because you have to know how data are distributed in a real world. For example, if you know that if your sample collects 30% and women and 70% of men, and you know that in the real world there are 15% of each of them, then you are giving the weight to men or women according to your sample and according to your prior knowledge. And then go to the next slide? Yes. And when you decide the method, how do we choose or how we collect our data, and then it's crucial to have good labels. Yes, today most of the machine learning are supervised learning. Of course, they are unsupervised and supervised, most of them. So if we have supervised machine learning, we have to label our data. So one method which book discuss is hand labeling, but of course it could be expensive. It could be expensive. There could be some data privacy threats. It could be slow, and there could be label multiplicity. For example, it could be expensive because sometimes we need expertise knowledge. For example, if you do some kind of if you have some picture, X-ray picture, we have to label and the patient has some kind of disease or not. In this case, we need some doctor or radiologist who can label it and whose time could be quite expensive and limited. So when it comes to label multiplicity problem, we have this kind of problem. I will not go too in deeply in each these types. No, just some of them. But for example, label multiplicity means could be caused because we have different sources of labeling, because some different teams could work on the same tasks, label same data, and because this different team members can have a different level of knowledge, there could be some biases, and then during training, we have to find out these biases, these mistakes, and solution is to train our team members again. So and do this labeling again. So because of this, hand labeling could be quite expensive and it could be quite slow. And more easier and cheaper are natural labels, which are quite often used nowadays. And it comes when a model prediction can be automatically evaluated or partially evaluated by the system. What does it mean? For example, if we have a system that predicts, for example, stock prices for next 2 minutes, and after 2 minutes, we can see the real stock prices, and we can model can evaluate how good this prediction was. Or there is could be another example when a model estimates the time of arrival for a certain route on Google Maps. And so after the end of the trip, the model already knows how good this how long this trip actually took, and how accurate was evaluate time prediction. So but yes, it's natural labeling or not always handy. And what we have to do when we don't have hand labeling and natural labeling, in this case, programmatic labels are coming. And the types of programmatic labeling are weak supervision, semi-supervision, transfer learning, and active learning. And what does a weak supervision? What's the difference between them? So, for example, weak supervision is when labeling can be done by software, and one of the examples is open source, which called the Snorkel, which was developed by Stanford. Yes, or you can develop by yourself write some kind of code, write some kind of algorithm, which will give some labels to your text, but mostly it leads to noisy data. And yes, one of the another type of programmatic labels is semi-supervision, and and in semi-supervision we have like small data, data sets which are already labeled, and according to this small data set we can label the big ones, bigger data set. Yes, and again, this again can be labels can lead to the like noisy data. Could you go next slide, please? How much time do I have? Yes, in this slide we have like we can see which method are most used by companies, and we can see that like companies mostly use natural labeling and hand labelings, and very quite rarely use programmatic labels. So this like some of the like methods are not 100 because of each one company can use like different types of labels. That's why this is 62, 63, and 30. So that's why. And so please, could you go to, yes. And one more challenge when you train the data in real world, it like is the class imbalance. What is class imbalance? Is a difference in the number of samples in each class. So of course our machine learning works well and perfect if we have like balanced data set, which means that in each class, if we have like classification problem, each class are evenly distributed. Now, but our models are not working so well, and so it's really difficult to train a model when you have like imbalanced data. And in the real world, data are really imbalanced. But there are some ways how to deal with this imbalanced data. So one of the ways, so it's important when dealing with the balance, considering this imbalanced data, it's crucial to choose correct evaluation metrics. For example, when you have imbalance classification problem, we don't have to look at like overall accuracy. We have to choose the precision, recall, and advanced scores. And in addition, just not choose the scores, we have to choose metrics can be good if you use them for each class individually, not for just positive or negative class. For each class, you have to have a look each metrics. And in practice, quite commonly are use ROC curve, but it's for imbalance classification models of precision and recall curve is better to use because ROC curve is more like relies on more like positive classes. So, and yes, and another way to deal with imbalanced data set is resampling. There are two ways of resampling. Undersampling, when you take the samples, some set of samples from your data, and oversampling when you copy and add these copied samples to your data. But there is, of course, drawbacks. Undersampling, when you do undersampling, you risk to lose some important information. And when you do oversampling, you risk to overfit on training data. And it's important in the book, book mentions that it's important to know that we should never evaluate our model or resample data because it cannot overfit. It could tend to overfit. Overfit problems. Could you go next slide, please? And what is data augmentation? So data augmentation more used in in deep learning. or neural network when we have very small data sets. In this case, like we do simple label preserving transformations, which means that we randomly modify an image while preserving its label. We just we have it means like we have like image can be different. We have like image where we have like eyes or we can like give different color to eyes, or we can change their like shape or whatever it is. So we modify image. And another way is perturbation. Weird noise, a small noise of and this while we are preventing the label. And
sorry, just because we're running a little short on time, do you want to just summarize very quickly the end of this chapter, and then I'll hand it over to
Okay. No, so these are like before we train data, we have to take into consideration. It's important how do we sample, how to label, and how do we deal with imbalanced data. This is the important and crucial part of like before training our data. That's all.
Thank you for that. Yeah. I'll hand it over then to Prabha for our 5th chapter, which I think will be the last one that we discuss today. Yeah, but I will post the link to, I'm just going to quickly put the link now to our part 2, in case you want to hear about the rest of the book. And I also invite you to read the book. Yeah, so I've just put the link to our meetup. I'll put that on the meetup page as well. And yeah, so please join us for part 2 as well. For now, I'll hand this over to Prabha.
Right. Hello, everyone. So this 5th chapter is about feature engineering. I'm sure like a lot of you have encountered feature engineering as a part of your data analysis and model training already, but I'll just walk through like all of the key terms that you need to be familiar with when talking about feature engineering. Yeah, so essentially what feature engineering does is taking your raw data and turning it into an intermediate form so that you can use it so that it's refined better when you're actually training your model on the data that's available to you. So a couple of ways you can go about it is handcrafting new features from your own knowledge or domain expertise, and or like any other way by combining different set of features that are available to you and such. Or else you can use unsupervised learning and other such methods where you train the model on the raw data and understand underlying patterns and figure out like new features from the existing data themselves. A couple of commonly used techniques in different domains, such as time series, images, and NLP is mentioned here. So personally, I work a lot with time series data, and I've used almost all of the techniques here at different stages and different parts of my career for, improving the data set available and imputing it in the way that's needed. So yeah, can we go to the next slide? So yeah, and this specific example is the one that's mentioned in the book. It's about NLP. And it's about how to convert like raw data that is a corpus of text into specific tokens, which could be like individual words, or n-grams, which is like a single word, or like two words together as a single unit, or 3 words together as a single unit, and use them for like dividing the corpus of data that you have into smaller units and use them as features for further learning and training. In this example, this talk about you have like word level n-grams where you split everything by word, and you can use techniques like tokenization or lemmatization to like standardize all of the data that's in the corpus. And there's also stuff like character level, which I've heard very less about. Like I don't know any specific use case where character level n-grams have been used, but in certain contexts, especially with emojis and stuff, character level n-grams have been useful. So that's just like a quick overview of it. A couple of major operations that you're going to have to deal with when feature engineering is you first start with like essentially looking at the raw data that you have, and then a lot of first thing that would pop up when you're looking at the data is if there's like data missing, and what if it is missing, so like why is it missing. So sometimes there would be data missing at random. For example, when like the example that's specified in the book is about how a certain gender would not like specify their salary or their weight. So this would be registered as empty or missing data from your raw data set. And this could be useful, like you can impute it if you have like other information. Sometimes data is missing not at random, whereas like the empty value could just be what it is. For example, middle name. A lot of cultures don't have middle names, so a lot of values for middle names could be just empty, and you can't really do anything with it in terms of like handling that part of missing data. And sometimes people just miss out on adding information, and that's called missing completely at random. So there's a couple of ways to handle this missing data that the book talks about. For numerical values, sometimes we use like mean, median, or mode of that particular variable or feature to impute missing values. This is sometimes useful, but it also has its pitfalls if there's a lot of skewness in the distribution of the variable. So you have to be a bit careful and have the knowledge of the domain as well as the data set that you're working with before you start imputing missing values. In text or other kinds of data sets, sometimes you can use like a default value. Sometimes even in numerical data, you can use default 0 to impute a lot of missing data. Again, this might also like skew your data distribution, so you have to be a bit careful before you start imputing it. And a lot of people tend to also delete rows that have data missing. This can be useful if the proportion of missing data is quite low. Or if it is quite significant, it's worth investigating why there's so much missing data. So imagine like 10% of your data set has a certain variable missing. It's informative to have, we don't want to accidentally delete a representative portion of the data set because they have missing data. So even while deleting, you need to understand if it's a significant proportion, why is the data missing for the specific percentage of the entire data set before you can delete it. Silke, the next slide. Yeah. Okay, and a couple of more standard operations that you can actually do with the raw data set is stuff like feature scaling, which becomes really important when you have different variables which have different units, different ranges, different like value groups and such. For example, if you're comparing income, you would have it in the range of like 10,000 to 100,000 or £1 million if you're lucky. Whereas if you're trying to compare that, if another one of your columns or features is age, that is quite limited. It would be from like 0 or 10 to like 60 or 80 or 100, depending on what the data set is representing. So in stuff like that, it's always useful to scale all of the components against their own mean or and variance, so as to have standardized scales of measurement across all the features. So there's a couple of ways to go about it. Normalization, where you compress the data that you have between 0 and 1, or -1 and +1. So in case of -1 and +1, your mean would be 0, and then you would have just a max variance of 1 unit. Standardization works with the assumption that your data has normal distribution. So in that case, you would get you would start with the mean of the entire data set. For example, if you're working with stuff like heart rate, your mean would be like 60, and then you would have like a standard deviation and variance around the 60 beats per minute and around it. So yeah, sorry. And yeah, a couple of things to think about as well when you're feature scaling is if you have a very skewed distribution of a certain variable, stuff like a log transformation of the data before scaling is something that's very useful. So yeah, and most people work on feature scaling the entire data set that's available to them, but we'll learn later why this couldn't cause biases and why it's better to scale training data set separately from test data set, because otherwise we'll have like information from the test data set leak into the training data set, and that can affect like model predictions later on. Right, so yeah, sorry, just go back. Yeah, so another two techniques that actually become useful when working with different kind of data is discretization or binning. It is basically converting values with large ranges, columns with large ranges into discrete bins. I found them very useful when working with floating point numbers to like bin them into certain groups of certain values and actually use that for further model training. Another thing is a categorical, when you're working with categorical data, the model can't learn categorical data on its own, so it needs to be transformed into numeric values with techniques like one like encoding or like one-hot encoding. Sorry, yeah, one-hot encoding and such, so that model can actually be trained on it. Yeah, you can go to the next slide now. Yeah, and a couple of more operations that can be done on this data set is something called feature crossing, where you combine different features to create new ones. This kind of helps build new features where two features that don't have a defined linear relationship between them can be used as a single feature unit, and that can be used for model training so that it kind of improves the accuracies later on. Yeah, but there's a bit of con with it. So the new feature that you're creating with two existing features can be highly correlated with one of the existing features and can be further removed down at a later stage during feature processing or any other techniques for feature removal. So you need to make sure that when you're feature crossing, it's two unique features and they don't have high correlation with the new feature does not have high correlation with the two features that you have used. A couple of other things, I'll speak about them really quick. Embeddings, positional embeddings are essentially when we use text data and represent the text information as a vector in like ND space. And positional embeddings are used when the sequence of the text you're trying to learn about, the sequence of the words in that text is important, and you want to encode that information when you're trying to receive the output. And yeah, and discrete and continuous positional embeddings are what are being used currently in the newer models coming out, like with the BERT model and transformer models used for NLP training in the last couple of years. I think there's like just an introduction about these two techniques in the book, but I think there's a lot more resources online to understand more about them because of all the changes in the last couple of years. Yeah, and the next slide, please. Yeah, finally, we come back to important information about data leak. And essentially data leak happens when there's a part of the information from the labels that kind of leaks into the training data set, and it kind of creates a problem when you're trying to deploy your trained model in real world scenarios, because the label information or the existing like a part of the label information is not present in real world for your inference, and this can cause the model to fail eventually. So it's very important that the features that are going into training the model are actually highly independent of the outcomes. So examples of when data leakage can happen is if you're imputing data, missing data in the training data set with values that are present in the test data set as well, or only in the test data set. But if you're imputing on the entire data set before splitting the data set into train and test, that can cause a leak from the test data set, validation data set into the training data set. Another example is, for example, in like stock market prediction kind of scenarios, if you have time dependent data and you split your data set for test and validation, for training and validation with time independent splitting, and this can cause stuff where the future where you want to predict is actually in the training data set, and you wouldn't have that information in real world. So that can kind of cause problems and the model to fail when it's deployed in real time. So a couple of ways to detect this data leak. There's something called ablation study. I wasn't aware of it before I came across in this book, but it's essentially like removing each feature that is being used in the training data set and seeing how the model performance degrades over time. Degrades essentially, not over time. That kind of ensures or highlights which particular feature is highly important for the outcome, and helps us narrow down if this particular feature has any information about the outcome, and we wouldn't want that. Some other things is like stuff like subject matter experts or domain knowledge information about the data set can be really helpful to identify if we have outcome information in the training data set as well. And using techniques like stratified test and train based on what you would want to keep your training and testing separate. Which feature you would want to keep separate in your training and test is something that's also useful to prevent data leak. And I think this one more slide. Yeah, and then finally we come down to understanding essentially feature importance and generalizability of the features to like the unseen data set. So the problems with having too many features is that you have issues with real-time inference. There's more compute and memory that is needed to create these new features and then have an outcome from the models. Also, there's problems with overfitting the data when we are model building. The solutions are, as mentioned before, stuff like feature selection, using domain knowledge, correlation matrix, PCA analysis and stuff, so that you can essentially narrow down the set of features that you're using for model training. Statistical methods to retain informative features. You can do comparison study of which features are important and which are not. Also, identifying important features using techniques such as like I think most of the tree models have like they come up with a feature importance plot that you can see what percentage of a certain which feature and what percentage of importance it has. So those kind of information can help you narrow down your top 10 features or top 5 features that are needed and discard the rest of it so that your model doesn't overfit and you have like quicker response times when you're deploying. And it's also important that the features generalize well to unseen data, and they have good coverage what that essentially means is that the features, a lot of the data is present for this particular feature, and the distribution of the features that have good coverage are essentially does not have like a lot of outliers. It may or may not have normal distribution, but also it's important to understand what kind of distribution they follow, so that you can potentially identify any issues or biases in the feature in the data set itself. But yeah, I think that's it. I think that's all of chapter 5. If I've missed something, do let me know. But yeah, that's it.
Yeah, thank you so much. I think this chapter is very, very interesting, and I think I learned a lot as well. Just reading about kind of all of these ways to address like data leakage and combining features, and so yeah, I think it's well worth a read. And thank you for summarizing that. We're sorry for running over a little bit.
Sorry about that.
It's just no. It's just this book is so dense, and I think it's hard to cover everything.
Yeah.
But yeah, no. Thank you to everyone who joined, and thanks to everyone who summarized the chapter as well. And hope to see lots of you on. So it'd be the March the 24th is kind of part 2 of this to cover the remaining chapters.